that the last paper was to be presented by Fabio Ribeiro from Worcester Polytechnic Institute. Preparation, characterization, catalytic activity of nanoscale molybdenum carbide catalysts. Dr. Ribeiro.
Good morning. People are using this? I don't have to. Maybe I don't need to. Let me try to explain you this project first. This is funded by Office of Industrial Technologies, OIT. And the idea was to follow on the 2020 Vision 2020 report and come up. The idea was to come up with some new process. And a number of companies, Hyperion, what used to be Raytheon, and us, we submitted a proposal to try to use a special type of catalyst, which is you see on the frame of all the transparencies, this TEM of a carbon nanotube. And the idea was to make a special material. And we tried that in a number of reactions. You see today only hydrodesulfurization. But that was the idea, and I guess we should start by acknowledging the DOE Office of Industrial Technology. There is also Battelle is helping us with the characterization, the XPS. In Washington Group, their role is to run those, many of the reactions we are trying, they run it in industrial scale, they have pilot plants and so on. So the idea is a much more, it's an applied project. And the idea was to find a new catalyst, new formulation. So the outline of the talk will tell you a little bit about the transition metal carbides and nitrides. You probably, most of you are experts on that. In particular, the nanoscale molybdenum and tungsten carbides. Again, we studied both of them, but today we will talk about only molybdenum carbide synthesis and potential applications. Then characterization by TEM, SEM, and XPS. The reaction study that we'll show you is HDS of diaphragm. It's just to more to compare with literature values, and then we'll summarize for you what we accomplished. So the idea of using carbides and nitrides have been around for a long time. One idea is that it has special properties by putting carbon on the molybdenum and tungsten. You could modify the properties and make a material that's is much more interesting, has interesting properties. On those carbides and nitrides, we wanted to be able to prepare molybdenum and tungsten with a very on the nanoscale. There are many methods of preparing those carbides. The one we have been preparing has an area of about 60 to 200 square meters per gram. Potential applications for those reactions, we have isomerization. We tried the dehydrogenation of ethylbenzene to styrene, and right now we are on the HDS. So the carbide preparation methods, this is a material that's used in many other applications in industry. There is many uses for the carbides, for tools, etc. So there's a metallurgical preparation, involves high temperature, and the idea there is they're zeroing into mechanical properties. That's what they're interested in. In our case, we are interested in high surface area, also mechanical properties. And in this case, the carburization many times is done with a carbon source, CO, methane. We have a lower temperature. Sometimes we end up with free carbon, but the methods of addressing that free carbon are taking the heat away. And there are, of course, many other methods like chemical vapor deposition. So the objective of this project was to prepare nanoscale molybdenum and tungsten carbide with high catalytic activities. But the main thrust or idea was to use a carbon nanotube, which Hyperion makes in the hundreds of tons per year. We'll show you how those carbon nanotubes look like they have a very special properties, but the idea was to use those to support the carbides and the nitrides on them, and hopefully transform the nanotubes into a carbon molybdenum tungsten carbide nanotube. And we thought that those materials would have very interesting catalytic properties, and we tried a number of commercially interesting systems to validate those ideas. So for comparison, we tried other catalysts. There is what's Hyperion calls fibril nanotube. We abbreviate here by FNT. As I told you, they make these in hundreds of tons per year. As far as I know, I think this is the only company that sell those materials commercially. We also use an activated carbon, graphite, and as a carbon source also, sometimes we just take the molybdenum oxides and pass a carbon source, a gas carbon source, and prepare those materials also unsupported for comparison. And the molybdenum precursors, we use the oxides, ammonium-based ones, and the phosphorus molybdenum acid. So we use a number of precursors. Of course, our main interest is on the fibril nanotube. It's produced by catalytic decomposition of a hydrocarbon over a supported catalyst. As I told you, this is produced in hundreds of tons a year. They make those materials. They are highly entangled to form those fibril aggregates, and that's the way they wanted to do it. You see, showing the next slide, that there are many properties that depend on those properties. Everybody talks about the single wall carbon nanotubes, but you've got to remember that it's only one sheet of graphite. I guess once you start functionalizing this just one layer, then you destroy the tube that you want to work with. So this one is a multi-layer, and you can functionalize the outside, and you still have the structure of the carbon in the center. So this is manufactured in large quantities, and by functionalization you can change the chemical properties. You can make actually extrudates that has very good mechanical properties. It's a very high purity carbon, so it's can be used in a number of applications in catalysis. Many industrial processes use carbon as a support. So here is a more detailed picture of what it looks like. It's a little tube, and it has a multi-layer. And here is a TEM picture. Didn't come out very good on this transparency, but you can see here the many layers. Here's the central part of the tube, and here the other layers. So that's how it looks like. It has a length 1 to 100 microns. It's very large. The amount of catalyst that's there is very minimum. It looks very much like the polymer that, for instance, you use to make polyethylene. It's a very small amount, and this thing grows out of the catalyst. Diameter 8 to 10 nanometers. Looking at this, you may look like it's a long, large tube that's hollow inside. That's not the idea. You see the TM. Later on, it has many defects. And in fact, those defects are very important for the mechanical and chemical properties of this material. Surface area is quite adequate, between 250 and 300 square meters per gram. Very pure carbon, high crystalline order, excellent electric conductivity. I think most of the sales now for those polymers are for those materials. They add into polymers and make plastic. They become conductors. The mechanical properties are also very good. They can make extrudates of those things. So it's not that it's a very fine powder that will stay in a reactor. They can make just like a pellet that you can make with an oxide. Of course, very high thermal stability and chemical purity. So how does that material look like? We have here two pictures. One is on the left is a TEM, and the one on the right is SEM. So it's a highly entangled material. with the you see about the same thing with either TEM or SEM, and that's like I said, in many applications this is a nice feature. So let's start with the characterization results, and we have three different types of carbon: the fibril nanotube, the graphite, and the activated carbon. Now, the way that those catalysts were prepared, they were mixed with, in this case, with molybdenum oxide, the molybdenum trioxide, and we made a physical mixture between those compounds, and then they're heated at high temperature, and then that drives the molybdenum oxide directly in contact with the carbon to be transformed into molybdenum carbide. And here are the XRD results. The fibril nanotube, the only thing you see is the molybdenum carbide at the end. The graphite, you see the molybdenum carbide also. This is the line for the carbon graphite. But with the activated carbon, we see a mixture of molybdenum carbide, the dioxide, and also the molybdenum nano. So it's difficult to prepare on this particular methodology a good catalyst using the activated carbon. So if you use the X-ray diffraction to look at what we have, here's the reaction temperature. The molybdenum carbide phase on the carbon nanotube is about 8 nanometers. On the activated carbon, we got actually a mixture of things and pretty large particles of molybdenum carbide. And on the graphite, we got also a very large phase of molybdenum carbide. But of course, we are making the preparation at the exactly same way for purpose of comparison. Of course, you can prepare molybdenum carbides many other ways. You could, using this activated carbon, you can optimize it in preparing different ways. You'd get, I would guess, a much better, much smaller particle size. So here's the XPS characterization before and after reaction. This is the typical peaks of molybdenum oxide before reaction and the carbon impurity. And after reaction, there is also passivation, so this is not in situ, so the sample is prepared and we have to passivate. So you get now a mixture of, you see molybdenum oxide because of the passivation layer, and the molybdenum carbide appears here, and also the characteristic peak of carbon and carbide. If you sputter off the oxide layer, then the oxygen contribution disappears. So we have the characterization on XPS. Maybe the more interesting one is the SEM study. What happens when you prepare those materials? And you see there that the fibril keeps its shape. It keeps the same morphology. You cannot see the carbide here, but it's embedded into the molybdenum carbide, very small particles. So the important part is that we keep the structure of the fibril. And here is a much better picture, a TEM picture. Of course, those size of the particles depends on what is the loading that we have on the carbon. This is a low loading. Those are pretty large molybdenum carbide particles that are not representatives. You can see the small ones on the carbide. So this one has a small molybdenum to carbon ratio. So just I think it's 10% molybdenum per carbon. And we can see the free standing molybdenum carbide nanoparticles. We can also prepare a sample that is 100% conversion. So this is all molybdenum carbide. And again, you can see that on this SEM picture for a stoichiometric molybdenum carbide, that the final shape of the molybdenum carbide that you form is very similar to the one of the fibril that you start. So you can use the fibril as a template to make those materials. I guess that the people that are experts on this area, the people that do really the TEM, if you really want a confirmation that this is what you're making, you keep the structure. Here you zero in into one of the fibrils, and here are some defects that I mentioned to you that those carbon nanotubes have. They are not a nice straight tube. They have many defects, and so people they can recognize their material very readily because of those defects. But in fact, this looks like the molybdenum, the fibril. But if you take if you look at the lattice fringes of this material, it corresponds to the one that's actually for the carbide. So we know for many methods, many ways, XPS and XRD and now TEM, that this is actually molybdenum carbide that is formed. Well, now that we told you all about the preparation, we in a temperature of 400 degrees C, and we analyze the products with a gas chromatograph. Very simple. We just wanted to find out how those materials behave and compare with the rest. We do not pre-sulfide those materials. We just bring them to a reaction temperature and start H2S. And this is a material that has 34% of molybdenum as a function of time. So there's a typical curve, starts very high and decreases. And the reason it does that, it does two things. One, you are sulfiding the molybdenum carbide, which is what the active phase is, but you're also depositing coke on the surface. So that's what you see. There's a deactivation, and the product selectivity is given here as a function of time. Pretty typical of those type of materials. We compare the molybdenum carbide versus the molybdenum oxides. I'm not sure why the printer didn't want to print here, but this is the molybdenum carbide, this is the dioxide, and here is the trioxide. So what we do in this case, we start with, again, with the carbide, with the dioxide and trioxide. You can see that the carbide is much more active, and the reason for that is just this active surface area. You start with the oxide, you have to form the active area first, and they also low surface area. So you can see a much higher activity on those samples on the carbide, but there's very small difference on the selectivity, which means that the chemistry is all the same. But it's just a question here of surface area. We start with material with higher surface area at the beginning. So the catalyst activation, then we've tried that by with thiophene itself. What happens with the conversion as a function of temperature? Here we start with the carbide. Then you can see the activity comes up pretty soon. The oxide, the dioxide takes longer, and the trioxide even longer. It's no question that the carbide is easier to be activated when compared with the molybdenum oxide. So that's much better to start with carbide, even if you have a problem with surface area. And here is a plot with catalyst loading. What happens when you change the loading? Here is the 100% molybdenum carbide, and this is the loading on the molybdenum carbide in the fibril. And here is the time versus conversion plot. And maybe easier to look. It's here's all the catalyst molybdenum carbide and the rate per gram of catalyst. And you see this volcano type of curve, and the reason for that is that when you increase the molybdenum carbide, you put more and more molybdenum carbide, of course, per gram, you're making more and more active sites, so the rate tends to go up. But if you pass a certain level, then you start destroying the structure, and then you have mostly bulk tungsten carbide, and then you start decreasing the area. Remember, again, this is per gram of catalyst. This is a pretty industrial project. They are interested in producing things, so per gram or per unit of volume is what they are interested in, and it's very reasonable, this type of curve, because two things going in different directions: surface area decreasing, but number of sites increasing as the molybdenum carbide changes. The one that we like best is if we normalize those things. Here's again the HDS rate as a function of molybdenum carbide. Then here per gram, and here you see an effect of again loading, increasing the number of sites versus decreasing the surface area. But if you use, for example, CO absorption to count how much molybdenum carbide you have on the surface, they are not very much different. There is some difference, not much, but also it compares very well with the literature values of the same reaction. So I think we understand the chemistry well. It's just a question of a better material, or how to make support this material. The XPS, again, after the reaction of sulfidation. This is before reaction. Again, this is the molybdenum carbide that has a thin layer of oxide, the skin of oxide. So you see all the oxide peaks in the carbide peak there. And then post-reaction, here we have a map of what we have. We see molybdenum sulfide and the sulfur appearing, and the carbide is still there. So after reaction, we see that there is some sulfur on the surface, but the carbide is still there, because it's important, because the sulfide is the thermodynamically more stable species. So if you would, if time is not a variable, if you let it there forever, it will eventually become all molybdenum sulfide. But we think that this process of formation of the carbide into the sulfide is pretty slow. And the active catalyst has a small skin of molybdenum sulfide and a core of molybdenum carbide. So we have XRD analysis indicating the carbide structure remains after reaction. So that's our story. I will summarize what we found. The fibril nanotubes can control the growth of molybdenum carbide crystals and can stabilize those very small particles. It offers advantages over activated carbon and graphite, mainly because this is a very well-defined material, well understood, pretty uniform. And these highly dispersed molybdenum carbide have a comparable activity on the literature for HDS. And this is due to the formation of this thin skin of molybdenum sulfide on the carbide surface. Well, we already thanked our sponsors, and I would like to thank you for your attention. I'll be happy to answer your questions.
Questions, please. First question. Mark.
Yes. I have, in fact, two comments. First, on the synthesis. We have done that 10 years ago, this sort of synthesis by evaporating MO3 on carbon different supports, what we call the shape memory synthesis. But we have a problem. With silicon carbide, you can get nanotubes of carbides. With molybdenum carbide, you make what you do, but make little pieces of molybdenum carbide, but no nanotubes of molybdenum carbide. It would be much more interesting to make this sort of suit of NO2C. That is a common thing. Nothing really. I think if we want to do something very new and important for catalysis, we have to manage to make the tube. We are on the way to do it now. Nanotubes of molybdenum carbide. It's much more difficult than to make that. That is almost straightforward to do. The second point is when you start about the HDS. In fact, we have also tried this thing.